So within this revision video, we're going to examine the causes and characteristics of seismic activity and also explore some of the hazards that we associate with earthquakes. Firstly, we're going to start by thinking about what an earthquake actually is. We can define it, as we can see on the left here, as the shaking of the Earth's surface, and that normally results from the sudden release of energy that has been built up and is stored within the lithosphere. That energy is released in the form of seismic waves, which we'll see a little bit more about in a minute. And when that energy reaches the surface, it causes the ground to shake. The strength of that shaking is going to vary depending on a number of factors, such as the amount of energy being released, how close you are to the epicenter or the focus of the earthquake, and also even down to the soil characteristics or rock characteristics of the land that you might be on. If we turn our attention to the map on the right hand side, each of the red dots on there indicates the location of an earthquake that has happened around the world. And we can see that the broad pattern is that those earthquakes tend to be found at plate boundaries. Earthquakes are present at all types of plate boundaries. So for example, we find them at destructive boundaries, where perhaps the Nazca and South American plates are converging. We find them at constructive plate boundaries, such as perhaps where the North American and Eurasian plates are separating here, or in the East African Rift Valley, where the African plate is splitting itself apart. We also find them at collision plate boundaries, where two bits of continental crust are colliding. For example, where India is moving north into the rest of Asia along the Himalayas. And we also find them at conservative plate margins, where one plate is moving sideways relative to another. So for example, with the San Andreas fault, the Pacific plate is moving faster than the North American plate. Or in the example of Haiti, where the North American plate and Caribbean plate are moving side by side. So earthquakes are found at all of the major plate boundaries, and we need to make sure that we're happy with the processes going on at each of those boundaries which cause earthquakes. So if you're not sure about any of that, go back and have a look at that sort of stuff within your notes, or go back and rewatch some of the videos about each of the plate boundaries. So it's not enough just to know the geographical location where we expect to find earthquakes. We need to consider how those earthquakes might be interacting with large or vulnerable populations. So the map on the board looks a little bit unusual, and it's because the size of any particular country or region has been either inflated or deflated relative to its population size. So somewhere like the UK, for example, with quite a large population density, we have been inflated in comparison to how we might normally look on the map. Somewhere like Australia, for example, down here, looks very different. It's deflated because it's got a relatively sparse population. The map in the bottom right hand corner here is obviously the world map for reference, and the density of earthquake intensity is shown here on this scale. So anything in red has a particularly high incidence of earthquakes. So there are some areas that stand out around the world as being particularly vulnerable to seismic activity. Places like California on the west coast of the USA, Central America, including quite large megacities like Mexico City, parts of the Caribbean such as Haiti, and most of the west coast of South America as well, so through Ecuador and Peru and Chile, where we have that subduction taking place of the Nazca plate beneath the South American plate. We actually have quite extensive seismic risk within parts of Europe as well, and certainly where we start to move from Europe into Asia. So through parts of Greece and Turkey and across into the Middle East, in countries such as Iran and Pakistan and Afghanistan. That's another area of quite high earthquake frequency, overlapping with a large and vulnerable population. We also have significant earthquake activity in the north of India and the west of China as well, where the Himalayas are found. And then finally, if we think about the Pacific, countries such as Japan, the Philippines and Indonesia all also experience quite significant earthquake risk. So we can see that it's not a risk that is evenly distributed amongst the world's population. Even some areas that experience earthquakes, like Iceland or the East African Rift Valley, they are not as vulnerable because the size of those earthquakes is smaller and the population is therefore not as at risk. Turning our attention then to the characteristics of earthquakes, it's important we perhaps define a few key bits of terminology associated with any earthquake. First thing to consider is the fact that all earthquakes occur along a fault line. A fault line is simply a weakness within the Earth's crust or within the lithosphere, where two pieces of the Earth's crust can move relative to one another, whether that's up or down or sideways. So ultimately a plate boundary is a very big example of a fault line. In reality, each plate boundary is surrounded by lots and lots of smaller faults which accommodate the movement of the two tectonic plates. So in this case we can see in this example one block of crust on the left hand side that's able to move in one direction, and the block of crust on the other side of the fault is able to move in another direction. Most of the time those faults are locked together and the frictional forces between the two bits of crust hold the fault in place and stop it from moving. But over time the pressures and forces build up to such a point where the fault slips, and it slips very suddenly, and the forces holding those two blocks of crust together give way. That movement releases large amounts of energy, and the point within the crust where the energy has been released from, in this case here, we call that the focus. That is the name given to the point within the crust where the energy of the earthquake is released. The energy moves away from the focus in the form of seismic waves. We're going to look in detail at the different types of seismic wave in a moment, but just like ripples in a pond spreading out in all directions, that seismic energy is transferred in all directions through the crust. So it doesn't just go upwards, it will go sideways and down as well and travel through the entire lithosphere. Ultimately, that seismic energy is going to reach the surface, and the point directly above the focus on the surface, which is closest therefore to where that energy has been released, is known as the epicenter. That's the term you may hear quoted if you hear about earthquakes that happen, you see them reported on the news. The location of the epicenter is very often the point that is recorded or reported. So you hear about people mentioning that an earthquake has occurred and the epicenter was 10 kilometers outside of Los Angeles. The point they're referring to there is this imaginary point, if you like, on the surface, which is directly above the focus. The reason we're so interested in that is because that's where the shaking or the intensity of the earthquake is likely to be greatest, because the energy has had the shortest distance to travel to reach that point, and therefore the energy won't have been absorbed or dissipated on its way. Somewhere else, such as over here, by the time the seismic waves have travelled that distance, they're likely to have lost some of their energy, and therefore the shaking is going to be less intense as we move away from the epicenter. Earthquakes share the same characteristics as lots and lots of other natural hazards, and that is that the higher the magnitude of the event, the less frequently those events are occurring. So these numbers here show you the relative magnitudes of different earthquakes and the numbers of earthquakes that we might get of that magnitude in any particular year. So we can see the lower down that list we go, if we're thinking about magnitude 2 earthquakes, we might get over 1 million of those earthquakes happening in any one year. They're very, very small, hardly even felt by people, and they're happening almost constantly. As we go up that scale of magnitude though, and we're increasing the size and intensity of that earthquake, the number of earthquakes diminishes quite significantly. And we'll see a little bit about why that is later on. But we can see once we get up to magnitude 7 earthquakes, we might have only a dozen or so of those in any particular year, and it's very rare that we might even get an 8 or higher more than once in any particular year. So there's that common relationship between magnitude and frequency, that larger magnitude events tend to occur less often. Two other characteristics that it's worth being aware of associated with seismic activity are the difference between earthquake storms and earthquake swarms. The picture on the left gives you an example of an earthquake storm. Okay, this is where earthquake activity moves along a fault line over a series of years. So an earthquake in one location will build up stresses on another part of the fault line, causing that area to experience an earthquake maybe 2, 3, 5, even 10 years down the line. This example here shows the example of the North Anatolian Fault. It runs through the north of Turkey, makes its way actually towards the city of Istanbul, a very densely populated city. There was quite a significant earthquake on this boundary in the 1990s, the late 1990s, 1999. The city of Izmit experienced a sizable earthquake, magnitude 7 earthquake. And we can see that in the past, earthquake activity has moved along the fault line broadly in the direction of Izmit. Okay, so in 1939, this green section of the fault was affected by an earthquake. Then in 1942, this brown section. In 1943, this purple section here. In 1944, this orange section actually went back a little bit the other way in 1951, then 1957, then 1967, and then finally in 1999, this earthquake struck the city of Izmit. And scientists actually had predicted, or certainly forecast, that Izmit was the next part of the fault line that was likely to be affected. Unfortunately, nothing was really done to prepare for or to mitigate against that, and tens of thousands of people actually died in that earthquake. So earthquake activity can move along a fault line. It's different from the concept of an aftershock, because these earthquakes are happening many, many years apart. So it's not that one earthquake has kind of triggered another one, but one earthquake has built up the stresses along a fault line and simply transferred, I suppose, that stress from one place to another when the earthquake has happened. It's a little bit like poppers on a shirt or buttons on a shirt. If you were to pull the bottom of the shirt, one of those buttons would pop, and then it would transfer the stress to the next button, and that would pop, and so on. And very slowly you'd get that unpopping of all those buttons, and the same thing happening along this earthquake fault line. Slightly differently is the concept of an earthquake swarm, which we have an example of here. This is on the Indonesian island of Lombok, and you can see here they were hit by 29 earthquakes over 4 on the Richter scale in a very short space of time. In the space of about a week or so, they were hit with 29 different earthquakes, all of a very similar magnitude. So most of these earthquakes are between 4 and 5 or 5 and 6 on the Richter scale. So it's not that we have one large earthquake, such as a magnitude 7, followed by lots of small aftershocks of magnitude 3 or 4. We've got lots of earthquake activity clustering themselves in a similar location over a similar period of time. Very often this is associated with the buildup of volcanic activity. Okay, so Mount Rinjani here, active volcano on the island of Lombok. These earthquakes are likely to be an indication So these earthquakes are likely to be an indication that that volcano was building towards an eruption. So if we turn our attention now in a little bit more detail to seismic waves, we can understand a little bit about their characteristics and therefore how we can also use what we know about seismic waves to help us with earthquake prediction. When the energy is released from the focus of an earthquake, so let's imagine we have the focus of an earthquake here. When that energy is released in all directions, like I said earlier, a bit like the ripples of a pond, and that energy radiates outwards from the focus. The rocks are moving in two different ways. They are experiencing, if you like, different movements depending on the type of wave that is actually transferring that energy. So both of these waves are released at the same time. P waves and S waves are released from the focus when that energy is released from the earthquake. P waves have a compressional movement, and a little bit like an accordion kind of squeezing together. The layers of rock are squeezed and then released, and the energy is transferred through the rocks through that compressional motion. It's known as what's called a longitudinal movement. You may have come across that in some science work or some physics work you might have done before. The crucial thing about P waves is there is very little ground movement. So when a P wave is detected at the surface, it'll only be picked up by a seismometer. You wouldn't be able to feel the arrival of the P waves. They travel very quickly, and the S waves travel slightly more slowly. So a P wave might be traveling kind of 6 to 8 kilometers a second. An S wave might be traveling kind of 4 to 6 kilometers a second. So it's not slow, but it's slower than the P wave. Now you'll notice that the S waves are moving in the same direction, but the way the energy is moving is very different. So this type of wave is known as a transverse wave. That movement, where we can see it moving up and down, is known as transverse movement. And actually that is what causes the ground to shake. So when an earthquake occurs, energy is released from the focus. The P and S waves race towards the surface. The P waves arrive first. They cause almost no ground movement, and then shortly after that, a few seconds later, the S waves will arrive, and that's what creates the rumbling and the shaking of the ground. Now, there is another set of seismic waves as well, but rather than them moving from the focus to the surface, like P and S waves do, these move from the epicenter. They move from the epicenter out across the surface, away from the epicenter. So these two here, love waves and Rayleigh waves, they are also referred to collectively as surface waves. So they have a couple of different motions. They can either have this kind of side to side motion, which again is a transverse type movement, or they can have this kind of rolling motion, a little bit like waves do within the ocean, the way that water moves within the ocean. And we get a sea wave, and you can imagine and appreciate that this causes the ground to rise and fall, or in this case the surface to move sideways, which again, both of these are going to cause lots of ground shaking and also quite a lot of destruction. So most of the damage done by an earthquake is done by these surface waves. Now we can use the characteristics of P and S waves to help us in the early warning systems that we might use ahead of an earthquake. You can think about P and S waves as a little bit like a firework, or possibly thunder and lightning, whereby both the sound and light energy are released at the same time. So when the firework explodes, or where we have a storm and we have some lightning, the energy is released at the same time, but the light energy travels faster than the sound energy. So we see the flash of the lightning or the flash of the firework before we hear the bang of the firework or the crack of the thunder. And the same principle applies with P and S waves. So we think about in this situation here, there's been an earthquake in this epicenter here, this focus here, and the seismic energy has been released. P waves are traveling quicker, so they hit the surface and are picked up by a seismometer. That seismometer recognises that it's a P wave and therefore knows that the S waves are not going to be too far behind. Instantly sends a quick signal to a computer. That computer then makes sense of that signal and sends alerts to everybody's house or everybody's mobile phone just in time for the arrival of the S wave. So this may only give 20 or 30 seconds warning between the P wave arriving and the S wave arriving. That might only be a matter of a few seconds. We're not talking about long-term prediction here, but that can be enough just to give people early warning that that earthquake has happened and that the shaking is on its way. So just like when we see a flash of lightning, we know the roar of thunder is on its way. The same principle applies here. The seismometer can pick up the P wave knowing that the S wave is on its way. So we can now turn our attention to thinking about the scales that we use to actually measure earthquakes. So there are two different ways that we can think about measuring an earthquake. One of them looks at the magnitude of the earthquake, and the other considers the intensity of the earthquake. Now they are measuring two different things, and we often will find that both figures are quoted for any given earthquake. If we start by considering the magnitude of an earthquake, we use the moment magnitude scale. Sometimes you will come across that abbreviated by the letters MMS, moment magnitude scale. So this measures the energy that is released during an earthquake. It's a calculation based on scientific measurements, which gives a number which indicates how much energy has been released during an earthquake. The moment magnitude scale was based on the Richter scale, and sometimes you will still hear people use that term Richter scale as a means of representing the size of an earthquake. That is a little bit outdated, and we don't really use that term anymore. So we want to be talking about the magnitude of an earthquake, or its MMS. The scale, however, shares some similarities with the Richter scale, such as being a logarithmic scale. I'll say a little bit more about that in a moment, but basically, when you go up that scale, you are not going up arithmetically. So the difference between 2 and 4, for example, is not double. 4 on the Richter scale, or the moment magnitude scale as it's now called, is not double a 2. It's actually 1,000 times stronger than a 2. So when we're going up that scale, we are increasing the amounts of energy very, very significantly. And that's why we don't tend to find very large magnitude earthquakes happening that often, because the amount of energy needed to build up to those big earthquakes takes a long, long time to accumulate in the crust. The MMS, or the magnitude of an earthquake, is recorded and determined using seismometers. These are sensitive computers that record the ground motion, and by working out how much the ground has moved, they can then calculate how much energy was needed to cause that much ground motion. In theory, the moment magnitude scale is open-ended. It could go as high as we like, 10, 11, 12, 13. There's no limit to that upper scale, but we've never had an earthquake recorded larger than 9.6 on the moment magnitude scale. And again, that's because to get above a 9 point something, we have to have significant amounts of energy being released. So the moment magnitude scale, that's dealing with the amount of energy that's being released. The modified Michaeli intensity scale, sometimes we will see this abbreviated to MMI. Okay, this is thinking about how damaging or how destructive or how fierce the shaking is within an earthquake. So we're more concerned here with measuring the sort of effects that an earthquake has, and it's based on people's observed effects and what actually happens as a result of the earthquake, rather than just being a scientific calculation. This scale ranges from 1 to 12. I'm going to show you an example of it in a minute. And we use Roman numerals within this scale to help us distinguish between the two types of scale. So you'll see sometimes a number like 7.4 followed by a rating on the modified Michaeli intensity scale. And each of those ratings from 1 to 12, as well as having that Roman numeral, it also has a certain title attached to it. So 10, for example, is extreme. Now, the values of this measurement are going to vary with distance from the epicenter. So closer to the epicenter, the shaking is going to be more intense because you're closer to where that energy has been released. And then the further away from that epicenter you go, the less extreme or violent that shaking is going to be. So the values might actually vary from place to place within the same earthquake. However, there would only ever be one measurement of the magnitude of that earthquake. Finally, as it said earlier about us basing this information on observations, this is really only useful to us in inhabited areas because we have to have people there in the first place to actually make the observations, and we have to have buildings there to be affected and so on. Now, to give you some indication about how some earthquakes compare, I've just picked 3 earthquakes here which are similar in magnitude but perhaps different in intensity, or similar in intensity but different in magnitude. So if we firstly compare the Haiti earthquake of 2010 with the Tohoku earthquake in Japan in 2011. Haiti was a 7 in terms of its magnitude, Japan was a 9. Okay, so the earthquake in Japan was 1,000 times stronger than the earthquake in Haiti. 1,000 times more energy was released. However, both of those earthquakes actually had the same intensity. That again comes down to lots of different factors, but primarily because the earthquake in Haiti was quite shallow, whereas in Japan it was quite deep, and therefore that's going to have absorbed some of the energy before it's reached the surface. And Haiti, the buildings were very poorly constructed, so that meant it was more damaging than it might have otherwise been. So 2 earthquakes here with very, very different magnitudes can actually have the same intensity. Likewise, if we compare the earthquake in Haiti with the earthquake in Nepal, or the earthquake in Japan, the earthquake in Nepal, we can see that for Haiti, a magnitude 7, but Nepal, a magnitude 7.8. So it's almost a step higher in terms of its magnitude, 7 and almost an 8. So if we think back to here, it's 32 times the amount of energy being released. However, when we look at its intensity, it's actually less than Haiti. It was only an 8. Even though the magnitude was larger, it actually had less intensity than the earthquake did in Haiti. So that's why it's important for us to use both of these scales when we are considering earthquakes. We don't just want to consider one scale because it only tells part of the story. So this diagram here might look a little bit confusing, but this can help us to understand that relationship between the magnitude of an earthquake and the energy that is released. So if we think about the rating on that moment magnitude scale, we can see that as we go up one of those scales here, so from a 2 to a 3, for example, we are increasing the amount of energy here by 32 times the amount of energy. So magnitude 2 might release 56 kilograms of explosive in equivalency of energy, whereas a 3 would release 1,800 kilograms of explosive equivalent. If we went from a 2 to a 4, as I said earlier, this is not doubling the amount of energy released, we are increasing it by the factor of 1,000. So 56 here, 56,000 here. So you can see that as we go from a 2 to a 3 to a 4, 5, 6, 7, 8, 9, bearing in mind our largest ever earthquake recorded was a 9.6, we can see that we are talking here about really, really significant amounts of energy. So no wonder we don't get earthquakes really going beyond this 9 point something level on the magnitude, because in order to build up this amount of energy, we would have to have that energy building up for such a long time, and the crust isn't really able to withstand that amount of energy building up within it. In terms of the intensity then, this table here shows you those different levels from 1 up to 12 in terms of the modified Mercalli intensity. You can see right down at one end, 1 is just what we would call an instrumental earthquake, as in it's only picked up by scientific instruments. Okay, so it's not felt by people. Moving through weak or slight to moderate, so this might be just felt indoors by many people. Some people might wake up, dishes, windows and doors might rattle and walls might make a cracking sound. Moving then up towards a 7 or an 8. So an 8, remember, was the rating for the Nepal earthquake. So damage is slight in structures that are well designed but considerable in normal buildings. Damage great in poorly built structures. Brick buildings easily receive moderate to extremely heavy damage. And then moving up towards the top end of that scale, that's where many well-built structures are destroyed, or few if any structures remain standing, up to a 12, which would be total destruction, where everything is destroyed. So Haiti and Japan in 2011, both a 9 on that scale. So we can see we're using slightly more kind of observational categories here when we are looking at the intensity of the earthquake. Final thing to cover then are the different hazards that are associated with earthquakes. Now, ground shaking is obviously the most significant thing that we associate with earthquake activity, and the amount that the ground shakes will vary on a number, depending on a number of factors. So firstly, how close you are to the epicenter, as we've said, but also on the rock type or the soil type. Different rocks and soils can actually allow the earthquake energy to pass through them more easily and therefore make the shaking more intense. As the ground is shaking, it's also moving up and down or moving from side to side, and that can cause either uplift or subsidence, as we can see in this picture here, where part of the road has either moved up or moved down, or where part of this train track has moved from side to side as a result of the shaking of that earthquake. So we can get lateral or vertical movement of the ground along a particular fault line. Now, while that's maybe disruptive for roads and railways to end up like this. If we think about the foundations of a building being exposed to these kinds of stresses, of being sheared from one direction to another, or part of a building rising or another part of it subsiding, we can see how the foundations of a building are not going to stand up to those kinds of stresses. The ground shaking can also cause mass movement, so either in the form of maybe landslides or rockfalls. These are quite common in steep mountainous terrain such as the Himalayas, for example. We can see here, following the earthquake in Nepal in 2015, all of that debris that's come down the side of that mountain, huge boulders that can obviously block roads and crush houses and kill people, and be really, really difficult in terms of then getting aid or supplies into those areas. We also have to consider as well in mountainous regions the danger that's posed by avalanches. So if these earthquakes are occurring in the winter months, large amounts of snow on the side of mountains can be dislodged as a result of that ground shaking. Quite famously, during the Nepal earthquake in 2015, there was a large avalanche at Everest Base Camp, which was actually really, really damaging, and avalanches killed quite a few people who were climbing Mount Everest that year. As well as this side-to-side motion, or this vertical motion impacting on railways and roads, it's going to impact on things that are buried beneath the ground as well. So if we think about gas pipes rupturing as a result of those gas pipes breaking, then fires can break out as a result of that, and those fires can then spread very, very quickly through buildings, and again can be a sort of secondary hazard, which can be very, very deadly in the form of earthquakes. Another unusual hazard that we find associated with earthquakes is the process of liquefaction. This occurs where saturated soil loses its strength as a result of being shaken. The shaking basically causes the water within the soil to rise to the surface, and the soil behaves a little bit like a liquid, really, and becomes almost like quicksand. And we can see how this car has actually sunk into the ground. This, before the earthquake, wasn't muddy. This would have been maybe some grass, or even a little bit of road outside someone's house, and the result of the shaking of the ground, it's liquefied, it's turned to liquid and basically swallowed up that car. So as disruptive and frustrating as it will be for that car owner to come out and find their car like that, we also have to again consider the impact this has on the foundations of buildings. Very, very damaging, and buildings would struggle to remain standing in an area that's suffered from this sort of level of liquefaction. The final and probably most deadly hazard that we associate with seismic activity is actually that of tsunami. So these are large waves that are triggered as a result of earthquake activity. It can be formed in a number of ways, but the most common and certainly most destructive, leading to the largest tsunamis, is the example that we've got up here on the right hand side. So where we have a destructive plate boundary and one plate is subducting beneath the other, there's going to be friction being generated along that Benioff zone between the two plates. So that plate will become stuck and it will start to distort slowly. So rather than the plate being in this position here, indicated by this dotted line, the plate actually bends upwards, and very slowly that plate is distorting and bending upwards. And while it's doing that, it is storing up huge amounts of energy, which are then released as an earthquake, and the crust then flicks back upwards. So at this point here, rather than, as we can see in the diagram above, the plate being shaped like this dotted line here, it flicks upwards as a result of that earthquake releasing the energy. As the sea floor flicks upwards, it pushes all of the water that is above it, it pushes that upwards as well. And then that water races away in all directions towards the coastline and out into the ocean, bringing with it, or creating as a result of it, a tsunami. This diagram here gives us some idea about the characteristics of tsunami. When they are out in the deep ocean, and this isn't drawn to scale by the way, they have very, very long wavelengths, okay, maybe 100 or 200 kilometers from one wave to the next. To put that in context, a typical wave just out in the ocean created by the wind maybe has a wavelength of 100 meters. So 100 or 200 kilometers is a really, really sizable wave. They also have a very low wave height. In some cases, maybe only half a meter to a meter high, but 100 or 200 kilometers long. That makes them very, very difficult to detect because, as it says here, that very small wave height and very long wavelength mean that any monitoring equipment needs to be very, very sensitive to pick up those very subtle changes in the water. As the tsunami reaches land, or as it moves from the deeper water into the shallower water, just like any other wave, it slows down, and the bottom of the wave slows down. The top of the wave carries on moving at the speed it was before, and tsunami in the deep ocean can travel kind of 500 miles an hour or more, the speed maybe of a jet aircraft racing across the ocean. So as the wave approaches land, the wave energy is concentrated into a smaller space, and what that does is it causes the wave to grow in height quite significantly. So very often we don't see a tsunami until it actually reaches the coastline. One of the first things that will happen is that the water on the beach and on the coastline will be drawn backwards away from the sea, away from the coastline, to feed the growing wave that is coming in behind it. Those waves can vary in height depending on the amount of energy being released by the earthquake, but certainly 10 meters is not uncommon, and by the time you funnel that wave then between buildings or up kind of river valleys or into small bays, the height of tsunami can reach 20, 30, maybe even 40 meters with that funneling effect. So really, really significantly sized waves. The run-up of that tsunami, the approach of the tsunami towards the coast, is going to vary depending on a number of factors. So the size perhaps of the earthquake or volcanic eruption that's caused the wave in the first place, how far it's had to travel. If the earthquake has happened quite close to the coastline, less of that energy is going to be lost on the way. By the time a tsunami has maybe crossed the entire Pacific Ocean, it's going to have lost some of that energy. So the closer to the epicenter you are, the more destructive that tsunami is going to be. The water depth is important. If the water is very deep, the tsunami is not going to be losing much energy. And the topography of the coastline is important. We've discussed this when we've thought about tropical storms, how storm surges can be funneled and amplified by bays or inlets along the coastline. And that's no different for tsunami. Tsunami usually consist of a series of waves. There's more than one wave, and very often the largest wave is actually the fourth or fifth wave to approach the coastline. It's not that the first wave is the largest and then they get smaller. They actually tend to get bigger, and that's because about 40% of the energy is actually scattered back to sea, and basically the energy from this first wave is fed into the next wave, and then the energy from that wave gets fed into the next one, and the energy from that wave gets fed into the next one, and so they grow in height over time. So tsunami are very, very difficult to predict, very difficult to detect, and very destructive when they do make landfall because of the size and power of those waves. There is nothing really that we can do that's going to stand up to a large tsunami.